All right, so now let's look at the limit comparison test. The limit comparison test is going to be something that's intuitively, we've already talked about it in class, believe it or not, the limit comparison test. And the limit comparison test is basically something that I hope you find intuitive and very, very useful. I think the limit comparison test is actually much more useful than the original comparison test, despite the book's insistence on emphasizing the original comparison test. So let me explain what it is in detail, and then we'll see it in action a few times, and hopefully that'll help clarify. Hopefully that'll just help, answer whatever questions we have. So suppose that we have two sequences. So suppose we have A sub n and B sub n, which are two non-negative sequences. It's again important that everything is positive here, or 0. So these are two sequences that are both greater than or equal to 0. If we look at the limit A sub n over B sub n as n goes to infinity, and if this limit is equal to c, where c is some finite number, but c is positive, then it turns out that whatever happens to one series happens to the other. So the sum of A sub n converges if and only if the sum of B sub n converges. Okay, and so if one converges, so does the other. If one diverges, so does the other. The value that we get for the limit doesn't matter at all. It doesn't matter if this limit is 5 or 1 over pi. Most of the time, this limit's going to end up being 1, but it doesn't actually matter what this limit is. All that matters is that it's positive and that it's finite. Okay, and if that's the case, then whatever happens to one series happens to the other. And so let's look at something like n plus 7 over n squared plus 4n plus 3 as n goes from 1 to infinity. And what I want to do is I want to take this sequence, n plus 7 over n squared plus 4n plus 3, that's going to be my A sub n. So our A sub n is going to be n, it's going to be this entire thing in the sum, n plus 7 over n squared plus 4n plus 3. And what we want to do is we want to figure out, what can we compare this to? When n is large, what is this value approximately? And hopefully I've kind of primed you enough for this that you know that when n is a trillion, all that matters is the dominant terms. Okay, this is basically n over n squared. And so what that means is that we're going to compare this to n over n squared, or 1 over n, to make it even simpler. So our A sub n is going to be the original value in the sum, n plus 7 over the n squared plus 4n plus 3 term. And our B sub n, the thing that we compare it to, is 1 over n, because those are basically the dominant terms in the numerator and denominator of our sequence A sub n. And if you compute, if we look at the limit of A sub n over B sub n as n goes to infinity, this is the limit of n plus 7 over n squared plus 4n plus 3 divided by 1 over n. Okay, so divided by 1 over n. If we are dividing by 1 over n, this is the same as multiplying by n. This is the limit as n goes to infinity of, let's see, dividing by 1 over n is the same as multiplying by n over 1. So it's going to end up being n squared plus 7n over n squared plus 4n plus 3. And now when we're evaluating this limit, we could use L'Hopital's rule if we really have to, but just look at the leading terms. We get an n squared over n squared. When n is large, this is going to be approximately equal to 1. And as n goes to infinity, that gets closer and closer to 1. So this limit is 1. And remember what we're doing here. We're comparing A sub n and B sub n. And we took the ratio of those two sequences. We took the limit of that ratio. The limit was positive and finite. It happened to be 1. Like I said, most of these values will turn out to be 1 if we choose our sequence b sub n carefully enough. And because it's 1, what this means is that the fate of the sum n plus 7 over n squared plus 4n plus 3, what happens to that series is determined by what happens to 1 over n. Okay, and so these two series are either going to both converge or both diverge. And we know that the series on the right, that 1 over n from 1 to infinity, is the harmonic series. And we know that it diverges. Again, we've seen lots of proofs of this. And therefore, the original series diverges. Okay, so because the harmonic series diverges, and because that's what we compared our series to, the original series also diverges. Okay, and so that's how this is going to get used. Let's do a few more examples. Okay, so let's look at, say, the sum from 0 to infinity of 4 to the n over 7 plus 9 to the n. Okay, and so here, what I want you to notice is that the 7 just doesn't matter at all. Even when n is kind of small, even when n is like 10, the 7 just makes basically no difference to the value of the fraction. And so our a sub n is the original value in our sum. Our b sub n, the thing that we're going to compare it to, is 4 to the n over 9 to the n, or 4 over 9 to the n. We can check that the limit of a sub n over b sub n is 1. I'll leave that to you to check. And therefore, what happens to the series 4 to the n over 7 plus 9 to the n is the same as what happens to 4 over 9 to the n. And we know that this is a geometric series, and the geometric ratio 4/9 is in between -1 and 1. Therefore, this series converges. And what that tells us is that the original series, 4 to the n over 7 plus 9 to the n, also converges. Okay, so it's very nice, I think. You don't have to do this inequality business to get the comparisons. Sometimes the inequalities are necessary. So some of the examples that we talked about, like you had the e to the 1 over n, or sometimes if you have natural logs in there, kind of natural logs sometimes play better with the original comparison test versus the limit comparison test. But definitely when you have a rational function, like by a rational function, I mean a ratio of polynomials like n plus 7 over n squared plus 4n plus 3, definitely that plays very nicely with the limit comparison test. So that's, yeah, that's all I want to say there. And the last thing I want to do is I want to look at the sum from 1 to infinity of sine of 1 over n squared. Okay, so I want to look at sine of 1 over n squared. I didn't write that very well. Okay, and what I want to do is I want to think about what's something that we can compare to sine of 1 over n squared. And as usual, our a sub n is going to be the value in our series that we're looking at. Our b sub n here is going to turn out to be 1 over n squared. And what I'm thinking about is that when you take the limit as h or theta or whatever goes to 0 of sine of h over h, this is going to be 1. And so if we take sine of 1 over n squared divided by 1 over n squared as n goes to infinity, as n goes to infinity, 1 over n squared goes to 0. And then we end up back in this situation. We have sine of something over that something as that something goes to 0. And therefore, this limit's going to be 1. And therefore, sine of 1 over n squared, its fate is going to be determined by whatever happens to 1 over n squared as n goes from 1 to infinity. And of course, this converges. And therefore, the original series converges too. And that's the limit comparison test. Okay, and so that I think that's everything I want to say about the comparison test and some examples, the limit comparison test and some examples. We will do lots more examples in class. And otherwise, I think after we do those examples, we'll be ready to move on. Okay, so that's the comparison test.